5.4, the fundamental theorem of calculus. It is basically the thing that connects everything in calculus together. It's pretty awesome, actually. And I have another quick review here for you. Again, I would like you to go ahead and find these derivatives, turn it in for a 6-point quiz tomorrow when you walk in the door. Hopefully, you learned your lesson last time, those of you that didn't do it. What you will learn about: the fundamental theorem part 1 and part 2, the connection between the theorem and then area, and analyzing antiderivatives graphically. The fundamental theorem of calculus is the triumph of mathematical discovery and the key to solving many problems. This was a quote from a book written by Ross Finney and George Thomas Jr. It said, "If you were being sent to a desert island and could only take one equation with you, the derivative of the integral from a to x of f of t dt is equal to f of x," might well be your choice. That's how important this theorem is to calculus. Okay, part 1. A lot of textbooks differ between what is actually part 1 and what is not. It doesn't really matter. We just need to know that there are 2 parts. And this, in our book, is part 1. It says, if the function is continuous on a to b, then the function big F equals the integral from a to x of f of t dt. Big F has a derivative at every point on a to b, and the derivative of big F is equal to d dx of the integral from a to x of f of t dt is equal to f of x. And basically, we've been talking about that. We have been talking about the fact that the derivative of the integral of the function is actually the function, because the derivative and the integral cancel each other out. And this is just basically the fundamental theorem of calculus. It is that connection between integrals and derivatives. So we have a couple things that we want to make sure we take note of. We are talking about taking the derivative of an integral. We see this is the notation for a derivative. This is the notation for an integral. We need to make sure that what we are taking the derivative of, with respect to, is the same as the upper limit of integration. We also need to make sure that this lower limit is a constant right here. If those 3 things follow, then the answer is going to be what we get when we put our upper limit into our function. F of x is then our answer. So we're going to go through and do a couple examples here. We're going to go through and do one the long way. Alright, so we have the derivative of the integral from negative pi to x of the cosine of t dt. Let's just go through and evaluate this the long way and see why the derivative of the integral is the function itself. If I did find the antiderivative of cosine, the antiderivative of cosine is sine. So I'm evaluating sine from negative pi to x. Well, we know that if I have an antiderivative, I can just take my upper limit and my lower limit, put them in, and subtract my answer. So I have the sine of x minus the sine of negative pi, and put them in. Sine of negative pi is 0. Okay, remember the height, that negative pi would be 0. The derivative then of sine is what I'm trying to find. Well, we know that the derivative of sine is cosine. So instead of doing the long way, we can just remember the first fundamental theorem that says the derivative of an integral, my upper limit matches the variable right here that we are taking the derivative with respect to. My lower limit is a constant. We don't even care what it is. We just want it to be a constant. And that is our answer. So let's go back and do another one. The next problem we have is the derivative of the integral from 0 to x of 1 over 1 plus t squared dt. So we have the first rule taken care of. We are taking the derivative of the integral. The second rule, we want to make sure that this variable down here is the same as the upper limit variable up top. I want to make sure that my lower limit is a constant. Those three rules follow, so my answer is 1 over 1 plus x squared. I'm just taking my upper limit x and I'm putting it in for t, and that is my answer. Let's try this guy. We have the derivative of the integral, so that rule is taken care of. However, this is an x squared up top and this is an x. Same variable at least, but just not exactly the same. So we're finding the derivative of this function. Well, what did I do if I had a function inside of another function and I was trying to find that derivative? Well, we just used the chain rule. So my derivative would be what I get when I put the upper into the function. That's how we get the cosine of x squared. And then I'm just going to multiply on the derivative of my x squared, which is, you know, to be 2x. Final answer, 2x cosine of x squared. Very simple. You're taking your upper limit, no matter what it is, putting it into your function, cosine of x squared. And then you're chaining on the derivative of x squared, which is 2x. Because remember that we've talked about the fact that this integral right here is still a function. Up here is my variable, and we always would take the variable and we just multiply on the derivative of what's inside of that function. Alright, this one we have a slight problem because my lower limit is where my x is and my upper limit has the constant. Well, we know how to deal with that, right? All we have to do is just flip it around, because I know that if I can change my integral around to flip my limits, it just makes it negative. So now I have everything in line, x and x here. I'm just going to take, I have a constant on the bottom, I'm going to take my upper limit, x, and put it in. Final answer is 3x sine of x, but it's a negative in front because we flipped those limits around at the very beginning. Alright, this one is another one that's a little bit different. Now we have a variable on both the top and the bottom in terms of my limits. So let's go through and just talk about it. Neither limit of integration is a constant. So what we can do is we can actually split the integral into two parts. I'm going to take the derivative of this integral, but I'm going to say, well, okay, it doesn't matter what constant I use. So the integral from 0 to x squared plus the integral from 2x to 0 would be the same as the integral from 2x to x squared, right? I can just split this up using a constant, because the integral from 2x to 0 is going to, plus 0 to x squared is going to be the same as 2x to x squared. So then with him, I'll flip him so that my constant is on the bottom. So now instead of a plus here, we have a minus. And then I will just take my upper limits and put them into my function. I have x squared, so I have 1 over 2 plus e to the x squared times the derivative of x squared, which is 2x, minus then 1 over 2 plus e to the 2x times that derivative of 2x being 2. And when we clean it up, that is what our final answer is. 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. The fundamental theorem of calculus part 2. If f is continuous at every point of a to b, and if big F is any antiderivative of f on a to b, then the integral from a to b of f of x dx is equal to big F of b minus big F of a, also called the integral evaluation theorem. And what do you know? We've already been talking about this. So really, we have already talked pretty in-depthly about the fundamental theorem of calculus. We're just really trying to bring home everything now. To evaluate an integral, then you're going to take the antiderivatives and subtract it. Very simple. So we're going to really spend the next week, maybe even 2 weeks, trying to bring this home and make sure that you understand all of the parts of this. Okay, I also wanted to talk to you about the idea of total area. We have talked in the past about net area, and that the integral does find net area. We now, let's say we were given a problem and we wanted to find the total area, meaning taking all of your upper area and all of your lower area and adding them together, and so we'd be guaranteed to have a positive value in the end. Here's how we're going to do this. Let's say we have this example here of f of x equals 4 minus x squared. You can see that we do have a part of the function that is above the x-axis as well as a part being below. If I just found the integral of the function from 0 to 3, that would be giving me the net area. It would take whatever is down below and subtract it from the top. So we want to find total area. The easiest way, or the best way to do that, is to find your zeros. And we can see in this example we have a 0 at 2. Then we're going to integrate over those intervals of zeros. Some of those integrations will be negative if they are below. Some of them will be positive if they are above. We're going to take all of their absolute values and add them together. So here's the example I have here. We're going to find the 0 at x equals 2. And then we're going to integrate from 0 to 2 and from 2 to 3. So I have the integral here of 0 to 2 of 4 minus x squared dx. The antiderivative will be 4x plus 1/3 x to the third from 0 to 2. I put my upper in, my lower in, subtract them, I will get 16/3. That is the area of this top shaded region. If I do the same from 2 to 3, I will do the same thing, same antiderivative, put 3 in, put 2 in, I get negative 7/3. That is this area down below. It's negative because it's below the x-axis. To find the total area, I just take their absolute values, 16/3 plus 7/3, add them together to get 23/3, which is approximately 7.667. Okay? I would like to show you just how this does look in GeoGebra. There's a thing called the function inspector, which is in this window right here. If I click this drop-down menu, there's these options. There's a probability calculator. The function inspector is what we're looking for. Once you have that selected, you can just select the function you're talking about, and this window will pop up with some information about this function. I can move the points on this graph I know what's going on. I don't want him on there. Okay, so now I can move these points, and you can see that my numbers in my table off to the side are changing. Let's discuss why. If I go from, you can see my integral down here as well as the area. Right now, the integral and the area are the same thing, okay, because all of my area is above the x-axis. Once I get to 2, where we have a 0, again, I still have 5 1/3 as my area, as well as my integral. If I continue moving along the axis, you can see the difference now. My integral is getting smaller because this area below is taking away from my upper area. However, the area total is increasing, and we can see once we get out here to 3 on the end, we get 7.6667. However, my integral is just 3. The last thing I'd like to talk to you about is how to find the total area on your calculator. To find the area between the graph of y equals f of x and the x-axis over the interval from a to b numerically, this is how we're going to evaluate it. NINT, on our calculators it's called FNINT, and we're going to just put in, instead of f of x, we're going to enter in the absolute value of f of x, because what you should remember is absolute value makes everything positive, so that graph is now going to be flipped up to the x, to all being above the x-axis, comma x, comma a, comma b, close your parentheses. So I have the calculator here. Let's do that previous example. With the parabola question. If I put in here my home screen. We're going to put the function in. We're going to do the integral of the function with respect to x from 0 to 3. This will give me my net area, which is 3. However, if I do the same thing, and instead of putting in here just the function, I'm going to enter in the absolute value. You get that from your math key. Scroll over to NUM, your ABS key. That pops that in there. I need to, insert a 4 there. And then here, we're going to insert a parentheses to close that absolute value. And it's calculating that to be 7.66 repeating. The calculator is only going to get that close. It actually is 23/3. If I go to my y equals and I put in my 4 minus x squared, and I do 0 to 3, and I do a zoom fit, that's what the graph looks like. However, if I go back into y2 and I do the absolute value of whatever's in y1, when I graph that, it'll look exactly the same, except all of this is flipped up. And so now I could find the integral using my trace feature. Lower limit is 0, upper limit is 3, this is using y1, okay, and I could go back in. Let's put our bug on y2, our trace feature, number 7, y2, there we go. Lower limit is 0, upper limit is 3, and we see that it's 7.667. Okay? Alright, folks. That's 5-4. We're going to do a lot of explorations with this section. We really need to make sure you are pretty confident with it. So, have a good day. Bring your 6 points in tomorrow, and we will see you later. Bye, guys.